Okay, so we have to write a parametric equation for this. It hasn't mentioned what it is, but it's clear that it is a circle. The first thing I'm going to write down is that I know the center of my circle. Is going to be 1, -2, and my radius is 3. Now let's think about your circle parametric forms. So hopefully you remember those. It's x equals r cos theta and y equals r sin theta. Okay, so what I'm going to do here is I'm going to sub in my x value and my r value for each one. So here's my x value, here's my y value, and then we know r is just our radius of 3. So replacing those, I'm just going to get x minus 1 is equal to 3 cos theta, and y plus 2 is equal to 3 sin theta. And the idea is we want a Cartesian, a parametric equation. So if I rearrange this, I can just have x is equal to 1 plus 3 cos theta, and y is equal to minus 2 plus 3 sin theta. And there I have my parametric equations for that circle. Okay, the next one. We have find the Cartesian equation of the ellipse that has parametric equations of those. So this time it's an ellipse, and we have the parametric equations. We need to find the Cartesian equations, and then I'm just going to sketch the ellipse as well, just for some extra practice. So straight away, I'm thinking back to, alright, I know a Cartesian equation of an ellipse is in the form x squared on a squared plus y squared on b squared. So really, I just need to find a and b. I also know that my parametric equation of an ellipse is in the form of a cos theta and y equals b sin theta. So it's obvious straight away that a is going to be 1 and b is going to be 2, which gives me the parametric equation a squared on 1 squared plus x squared on 1 squared plus y squared on 2 squared. So I have x squared plus y squared on 4 equals 1. Now note, it's going to be our long ways, our vertical ellipse, as b is greater than a. So it's just something I'm going to note, just because I want to draw this for some extra practice. Now we've just got to work out, alright, well, what is going to be my focus and my directrix? And that all comes from knowing eccentricity. So we've got our eccentricity formula is a squared equals b squared bracket 1 minus e squared. Subbing it all in, I'm going to have 1 on 4, bring that over, is equal to 1 minus e squared. So e squared is equal to 1 minus a quarter. So e is going to be root 3 on 2. Now, notice here, the fact that it is going to be our vertical ellipse gives us 0 plus or minus BE instead of AE for your focus, and your directrix is going to be y is equal to plus or minus B on E rather than A on E. So therefore my focus is going to be 0 plus or minus root 3, and my directrix is going to be y equals plus or minus 4 on root 3. If I want to draw that now, I'm just putting everything on a diagram. So I say it is my vertical ellipse with 1 and -1, 2 and -2. Then we are going to have our asymptotes. And then our foci. which is 0 root 3. And there's my diagram. Okay, not too bad. It's just about remembering all of your equations for your parametric form and which one's the circle, which one's the ellipse, which one's a hyperbola, etc. Okay, the last one I want to look at is a tougher HSC question. So this question is the one we're doing here. It was in question 5 in 2010, so this is when they only had 10 questions, so it's halfway through extension 2 paper, which things are getting quite difficult at this point. Okay, so let's have a look at what it's saying here. So have a read of it. The best thing to do before you're approaching a question like this is to really understand it. Understand all of the information, the diagram, and what everything means. Okay, so hopefully you've had a look at that. Now part 1, it just wants us to write down the coordinates for B. So here's our coordinates for B. The first thing I'm thinking about is, straight away, things are in parametric form in the question, as it does tell us that point A lies on C1, it has coordinates A cos theta, A sin theta. So there's hints already that things are in parametric form, and the point here that A is A cos theta and sin theta. So coordinates of B, think about a circle. We know that the coordinates are just going to be your R cos theta and R sin theta, because we know that's on our unit circle, that's what it is. Now, just thinking about this smaller circle here in particular, it has a radius of B. Okay, so it's going to be a coordinate of lowercase b cos theta and then lowercase b sin theta. And all I did was just replace my R with the radius of that circle, which is B. So there's my coordinates for B. Part 2 then says, show that P lies on the ellipse. So show that that point P lies on the ellipse. Now, the idea is with that ellipse, we've got our point P. We don't really know what way that ellipse goes. So what we can just take is an assumption. By the looks of things, it's possibly going to be something like this. However, it could also be a vertical ellipse. All we know is that we have to show that it passes through this point P, or the point P lies on the ellipse. So basically, to prove that a point lies on a line is when you sub it in, it should be correct, okay? Or when you sub it in, the left-hand side should equal the right-hand side. So let's have a look then. We have a point P. Now, point P there is a point on the ellipse. Okay, so a point on the ellipse in parametric form, we know is given as A cos theta, B sin theta. Okay, so that's how we describe a point on an ellipse in parametric form. We should know that already from the last video. So then we have the equation of our ellipse that it's supposed to lie on is x squared on a squared plus y squared on b squared equals 1. So I'm just going to sub in my x value of a cos theta and my y value of b sin theta into my equation. So I've squared both terms because they're going to both get a power of 2. My a squared will cancel and my b squared will cancel, which gives me that cos squared plus sine squared equals 1. Therefore, P lies on the ellipse. What actually I might say before that is say therefore true by Pythagorean identity. And then therefore true, therefore P lies on the ellipse. Because that's our Pythagorean identity, cos squared theta plus sine squared theta equals 1. Okay, next one. It says find the equation of the tangent to the ellipse at P. So picture a tangent coming out from P. And I need to find the equation of that line. So, how do we find an equation of a tangent? Now, if this was my HSC, I would be showing the marker that I know how to do this. I know how to find the equation of a tangent. I'd write something like this. Differentiate. Then generally there you sub in your point. That finds you your gradient, and then point gradient formula. Not just for the marker anyway, but just for you to be able to step out your solution. You're not going to get too bogged down and get confused at where you're at and what you're doing. Okay, so we need to differentiate our ellipse. So we know that the equation of this ellipse is x squared on a squared plus y squared on b squared equals 1. Differentiating in terms of x and y means I'm going to have to differentiate implicitly. So differentiating in terms of x, I have 2x on a squared plus 2y on b squared times by dy dx is equal to 0. So don't forget with your implicit differentiation, when you are differentiating in terms of x, when you have to differentiate in terms of y, you put your dy dx on. Now my constant's going to go to 0, and now I just have to rearrange for dy dx. I'm going to have dy on dx is equal to negative 2x on a squared. And it's going to be dividing by 2y on b squared, which is the same thing as flipping and timesing. Okay, so all I have done is just rearrange for dy dx equals. My 2's will cancel and I'm going to end up with negative x b squared over a squared y. Okay, so there's my equation of the gradient at any point, but I want to know what it is at point P, and I know that from previously I said that point P is a cos theta, b sine theta. Subbing those in for my x and y, I'm going to have negative a cos theta b squared over a squared b sine theta. B will cancel a b, a will cancel an a, which gives me an answer of negative a cos theta over, negative b cos theta over a sine theta. And there is my gradient. Once I have my gradient, I use my point gradient formula. Y minus y1 is equal to m x minus x1. Sub in my point P. And like the last video, how I mentioned 2 times over that side and then expand the numerator on this side. I'm going to have ay sine theta minus ab sine squared theta equals negative bx cos theta plus AB cos squared theta. Get all my squares on one side. AY sine theta plus BX cos theta is equal to, factorize out my AB and I get cos squared theta. That comes a positive sine squared theta, which is really the same thing as timesing by 1. So I'm going to divide by AB. My A will cancel, my B will cancel, and I have y sine theta on B plus x cos theta on A is equal to 1. And there is the equation of the tangent to my ellipse at point P. Okay, last one. It wants us to show that the tangent to the circle C1 at A and the tangent to the ellipse at P intersect on the x-axis. So to intercept on the x-axis means they're going to intercept around here, because that's where my tangent goes through my x-axis. And I need to find out when the tangent there is going to intersect the tangent to the circle C1. So what that might mean is my diagram for my, take that out, my diagram for my ellipse might be out slightly. So we know we said it's most likely going to be something like this. If I do my tangent a bit more like that. So I know that there's where it intersects the x-axis, and the tangent on this circle has to also intersect the same spot. So I'm thinking, I mean, this is all just hypothetically, but I'm thinking that my point A is around here. So all I'm finding is the point of intersection between two lines. So go back to basics. Think, okay, how do I find the point of intersection between two lines? I solve them simultaneously. Solve what simultaneously? I solve the equation of each line simultaneously. I just found the equation of my tangent at P. So I need to find the equation of my tangent of the circle C1. Okay, so how do I find the equation of a tangent to a circle? Well, let's differentiate my circle. Okay, so the equation of that circle, so this is part 4. The equation of that circle is going to be x squared plus y squared, and what was my, where am I? The radius of C1 is A. So my equation of this circle is going to be x squared plus y squared equals a squared. And now I have to differentiate that. I'm going to implicitly differentiate a squared is just going to be some constant. Rearrange. And I get this value. So now I've differentiated. My next step usually at this point is to, if I can, sub in a point. Yes, sorry. So lost where I was at. Subbing in my point on the circle, my subbing in my point A is just going to be yes, okay. Going back to parametric of a circle, my point is going to be, I'll call it A. R cos theta, R sin theta. The radius is A, so A cos theta, A sin theta, which is going to give me negative A cos theta over positive A sin theta. And my A's can cancel, which give me negative cos theta on sin theta. So there's my my gradient. The last step then is to sub that into my point gradient formula to find the equation. So I'm going to have y minus A sin theta is equal to negative cos theta over sin theta, lots of x minus A cos theta. Same step again. Which then gives me my squares on one side. I'm going to get factorize out an A, and gives me the final solution of this equation. Okay, so there's the equation of the tangent to my circle. So I have just found, just to put it back into context, the equation of the tangent at A, the question before I found the equation of the tangent at P, and I need to find out, or I need to show that they both intersect on the x-axis, or in other words have a y value of 0. So I need to now solve them simultaneously to find that point of intersection. So we've got my two equations. I've got y sine theta on B plus x cos theta on A equals 1. And I've got y sine theta on A plus x cos theta on A equals 1. So solving these two simultaneously, I'm just going to rearrange one of them and sub it into the other. If I rearrange, let's go, it doesn't really matter, I'm going to get the same answer. But let's rearrange this right hand side one. Times my a to the other side, I'm going to have y sine theta plus x cos theta equals a. So y sine theta equals a minus x cos theta. And now I'm going to take that and sub it in here where y sine theta is. So I get that a minus x cos theta on b plus x cos theta on A is equal to 1. Now everything's just got x's and cos's in it, which makes my life easier. I just think about where you're going with this. I just need to find my x intercept, or my x value where they intersect each other, and sub it in and show that the y value is 0. That's showing that they intersect on the x-axis. So keep that in mind all the time. Don't forget where you're going, what the point of all this is. If I times through by, if I times everything by AB, that's just going to get rid of my denominators. Be careful of timesing everything through by AB. My b will cancel with this one, but I'm going to have a squared minus ax cos theta. My a will cancel that a, but then I'm going to have bx cos theta equals ab. Rearranging this, if I factorise out an x cos theta here, and I take my a squared to the other side, so I'm just going to factorise out, I've skipped a little line here, but I'm factorising this term here. If I do that, I'm going to have I'm going to have b minus a. If I factorise this right-hand side, I'm going to have a outside of b minus a. So therefore, x cos theta is equal to a. All right, at that value, I know that y sine theta plus x cos theta is equal to a. And if you can't see, that's just something I knew from this line here I wrote, which was rearranging this first equation. So I've restated that. And therefore, now that I know that x cos theta is equal to a, I can say, well then, y sine theta plus a is equal to a. So y sine theta is equal to a minus a. So y sine theta equals 0. So therefore, y equals 0. Therefore, intersection point. So therefore the intersection point occurs on the x-axis because that point y is 0, so it must be on the x-axis. So I think all I did there, from taking quite a difficult question, I just had to find the equation of both lines. I already knew one, so I just had to find the equation of the other line. And then I just solved them simultaneously, and I showed that they intersected on the x-axis by showing that the y value of their intersection point was 0. And that question there, you can see, is worth 5 marks halfway through your Extension 2 paper. It's not a bad 5 marks to be able to get. So that's the rest of that video. Let me know anyway how you go. Have a go at some HSC problems and see how you go with those ones.